Focus on recurrent neural networks, which is one of the most powerful models that you learn about in this class. Before we go into the lecture, the PSET was due at the latest on Sunday. I hope most of you were able to do it. We had a very low number of students who dropped the class, which is great. I'm very happy to see that. This is sort of the first time this class has been taught by me at Stanford, but really I think anywhere ever, in the sense that a pure sort of deep learning for natural language processing class wasn't around before. So we still have some kinks to iron out with the problem sets and so on. So thanks for sticking with us. So yeah, I think there are a couple of students maybe who are taking it for pass-fail who haven't turned in the homework yet. So if you do that and you now think, well, I'll just do really well in the project and the other problem sets, you do really want to get started really catching up with the class, and because all the other subsequent homeworks will require you to have understood sort of the previous things. So do come to office hours, do check out the code that I'll show today. In some ways we'll show some of the solutions to the first problem set and a nice sort of clean way to implement a two-layer neural network. Yep. All right. Are there any organizational questions around the problem sets or class progression? Yep.
How are we supposed to turn in that proposal?
How are you supposed to turn in the proposal? Boy, I guess.
You have to just put it in instructions. So the instructions are updated on the website.
Okay, so the instructions are updated on the website for how to turn the proposal. I think you'll update it, send it to box 2, or?
No, just submit it to the PDF to the source.
To the staff mailing list, or?
No, the score website.
Okay, great. All right. All right, any other questions? Great, so a little overview. We briefly mentioned language models, but I think I can give you some more intuition of how traditional language models actually work. And then I think you'll appreciate RNNs even more, because they don't make certain Markov assumptions that are quite unrealistic and traditional language models make. But not all is green on the other side in RNNs, because there are a lot of problems that they have too, namely the vanishing or exploding gradient problems. We'll try to gain a little bit of a mathematical intuition of why that is, and then show you solutions for fixing those. So again, RNNs are similar to other neural nets, where if you don't really know how to use them properly, you won't be able to get them to work. So here we'll cover some very important tricks for them, and then show you that RNNs are useful for more things than just language modeling. It really can do and solve a lot of other kinds of sequence tasks. And we'll go briefly into some extensions of RNNs, namely making them bidirectional, as in moving forward in time but also backward in time, and of course making them deeper, which in many cases helps. All right. Language models. So again, we want to basically compute the probability for a sequence of words, W1 to WT, some sequence. And this is very useful for machine translation. So here are two examples where a machine translation system might give you multiple outputs when it tried to translate French to English, for instance, and you now want to score them. So maybe you want to assign the sequence the cat is small a higher probability than small the is cat. Or in terms of word choice, maybe you want to assign higher probability walking home after school versus walking house after school. But both house and home might be reasonable translations of the French word maison or something like that. And word choice is particularly useful also for speech recognition, where you may have, I would like to know the price of wood. So now I have basically two things that sounded the same, wood and wood, but the price of wood and, I would like to know that kind of wood are different, and one would presumably have a higher probability in the sequence. All right, so how do traditional language models work? Basically, they condition on a window of n previous words, which is an incorrect but necessary Markov assumption. So in order to get the probability here for the entire sequence, we basically take the product of the probability for each of the single words in that sequence from 1 to m, And ideally, we would condition all the previous words, starting from the first one. But really, in practice, we'll approximate that in traditional language models by just taking a window of the last n words. And of course, that is a simplifying assumption that these kinds of models have to make, because the way they actually estimate these probabilities is by taking counts for specific sets of unigrams, bigrams, and generally n-grams that you see. So how do they actually compute the probability for a given word given its window? Well, if that window is just a previous word, so it's basically sort of taking counts of bigrams, then you would basically just take the counts of how often do you see word 1 followed by word 2 exactly in that order in your entire corpus, and then you divide by the number of times you saw the first word. And that will essentially give you the probability for the second word given the first. And if you wanted to go to trigrams, you would have to take all the counts for, word 1 followed by word 2 followed by word 3 and divide by the counts of how often you saw the first two in that order. So just to give you an example, so I wanted to say the cat walks. For instance, I want to get the probability for walks, given that I've seen the cat. So I basically take all the counts in a very large corpus, ideally the larger the better, of how often do I see the cat walks, and divide by the cat afterwards in those counts. So the performance of these kinds of models improves a lot when you can keep around higher n-gram counts. And then you do some smoothing and so-called backoff, where let's say you try to find if you have a 4-gram that you see exactly at test time. If you don't see it, you just look for the trigram. If you don't see that, you could look for the bigram and so on. And you may also combine all those. The problem is that there are a lot of n-grams as n gets larger. The upper bound is sort of the size of your vocabulary to the power of n. The number of n-grams. So there are really a lot of them, many tens of thousands of millions for tri and 4 and 5 grams. And so one of the most sophisticated ways to really store these kinds of counts is described in this paper by Ken Hatfield, Scalable Modified Knestrone Language Model Estimation. Knestrone is a specific type of smoothing. And there, after doing lots of tricks for storing these data structures and storing all these counts, he only needs a machine with 140 gigs of RAM. So just keeping around all these counts here in order to estimate the probabilities in traditional sort of discrete count-based language models takes a lot of RAM. And that is after an insane amount of research and optimization to put it into smaller, better, more efficient data structures. So, of course, now if you wanted to actually run your language model on your phone, or for instance, that would just not work, right? It's impossible to keep around all those counts as your corpus gets larger. But ideally, you want to train on larger corpora. The larger your corpus is, the better you can estimate what constitutes a reasonable phrase in the English language. So on the other hand, you have recurrent neural networks, which we'll go over now. Basically, the RNNs tie the weights at each time step, and there are different ways you can describe them. We went over them briefly in the last lecture, but basically they allow you to condition neural networks, condition the probability for each output given the entire sequence of words before by keeping around hidden state HT. So at each hidden state HT, we have a new word, XT come in, those will be word vectors, and now you want to predict basically the output, namely the next word at xt plus 1 will be your yt. Here, in that case, the RAM requirements only scale with the number of words, and you have basically a fixed set of weights W. And those W's could be large. You may want to have a hidden dimensionality of 1,000, so your W would here would be 1,000 by 1,000. So that's 1,000,000 weights. But the nice thing is, even if you have a train with a larger corpus, that will basically be fixed, and it still is able to incorporate more and more longer sequences and learn from a larger corpus. And really, the only thing, again, that increases is your lookup table, namely your word vectors. But there's no sort of exponential blow up in the number of n-grams. So in particular, this is the most standard definition of a recurrent neural network. We'll look at some others and modifications, but in the simplest case, we will basically have a hidden transformation matrix W here. That one always has to be a square matrix, and in here we map the word vectors into the hidden state of WHX. And so just to give you an idea here, we could basically rewrite this as, let's see where I am. We could rewrite that multiplication also in terms of having, first time I'm using this. Oh boy, that looks pretty terrible. So imagine, oh boy, I don't know if you'll, all right, let's just use the board. You have here WHH, and you could make one larger matrix, WHX, times your vectors HT minus 1 and XT. So now this matrix multiplication is exactly the same as writing out this here with the plus. Right? And if that doesn't make sense, you basically multiply each line, you add them up again at the end. If that doesn't make sense, do write that out with all the indices at home, and then you'll see that those are the same. Basically, we have just a hidden layer here. And then in this case here, we apply the sigmoid function, but really there are other choices later on. And then for each hidden state, we basically have the standard softmax, which in our case will predict the word for language models. All right, here are two other ways people describe them. I'm not a big fan of this loop way to describe them, but you'll see that in the literature and if you read papers also quite commonly. All right, so the main idea here is again that we use the same weights W at all time steps. That way, the sequence can be of arbitrary length, and we basically will be able to compute a hidden representation at every given time step. Everything else here is the same if we use language models. Here again, we just have a specific initialization vector for the hidden layer at time step 0. This is H0. We'll have different dimensionalities here for our hidden states and potentially the word vectors. And we'll have our softmax, in the case of language modeling, has the output of size of vocabulary. All right, so then we have our probability estimates here are over the entire vocabulary, and that allows us to use the same cross-entropy error that we had used before for various other classes. It just turns out the classes now are the words. So this is the same cross-entropy error, and here we look at time step t, we just sum over the entire vocabulary. Of course, we don't actually have to sum over the entire vocabulary, right? Because there's only a single word, but this is the full definition of the cross-entropy error. All right, it turns out you could just basically look at the overall, the negative average of the log probabilities over the entire data set size. So this is basically the cross-entropy error over the entire sequence, making all the single predictions at all the time steps and then just averaging that. But it turns out that most people prefer to take that amount here and to the power of 2, or the power of 2 of that basically negative average log probabilities, and then call that perplexity. And now you want a lower perplexity is basically better. The less perplexed you are, the more certain you are about predicting the correct next word. Yeah?
Can you give some intuition as to why that amounts to perplexity, like the word perplexity? So, like, perplexity means that, I guess, confusion, kind of.
Right.
So why does raising the cross-entropy, or taking 2 to the cross-entropy do that?
Right. So there are actually some nice intuitions from information theory, but the last time I brought that up, some people complained, and it's really not that necessary. So let's take it offline. But yeah, in general, you can kind of think of In this case, it is really not as necessary. KL divergence still was and will become necessary. But yeah, there's some nice intuitions there. But really, you can think of the more perplexed you are, the worse you're off. All right. So one of the main issues with RNNs is that it's also comes from the same advantage that we have of having the weights tied or having the same W matrix at every single time step. And so during forward prop, again, we have the same W here to compute every time step's hidden vector. And so ideally, in theory, if I have an output here at time step t 1,000, and maybe 200 time steps before, something really important happened, and I want now that to still modify what comes 100 or 200 time steps later. However, that is a very hard problem for RNNs to really be able to do. And so one thing I encourage you all to do is write out an RNN with just 2 or 3 simple time steps, and then really manually derive the gradients just like you did with single and 2-layer neural networks. It will be very, very instructive and helpful, insightful for you to do that. So let's look a little bit into the so-called vanishing or exploding gradient problem. So these are 2 different kinds of problems that may arise from having the same W here at every time step. Basically, because we multiply the same matrix at each time step during forward propagation, we'll have to do the same thing during backwards propagation. And so just to give you an intuition here, as we have an error term here at every single time step, right? So you have ET minus 1, ET, and ET plus 1. And now, if we want to minimize our error at ET plus 1, then we'll propagate those signals all the way through the network. So down to XT plus 1, and then to HT, and then to XT, and this basically continues. We keep propagating that error all the way until, in theory, the first time step. So let's try to write that all out, and in order to simplify some of the notation and analysis here, we'll have a slightly different RNN formulation, but if you write that actually out, it boils down to almost exactly the same way. We just apply the nonlinearities at a later step. So here we'll define our hidden step to be computed with just a linear transformation times a nonlinearity of the previous hidden state, plus our word to hidden matrix WHX times the word vector at XT. So now here, notice how I dropped the the superscript W here, just for notational convenience. And then we have here, we then basically apply the nonlinearity only when we compute Y, our prediction. And this is, again, could be the same softmax here, but let's, for simplicity, drop the softmax and just have linear scores. A lot of the math is very similar, but it'll be easier to write out. So now let's look at the total error of the entire sequence. Again, that will be the sum of the errors at every time step t. And let's take the derivative with respect to W, which is the hidden weights, and those, again, replicate at every time step. So now we'll have to go slowly because we'll apply the chain rule many, many times, and after doing it 3 or 4 times, you'll may get lost if you don't concentrate. So let's do the first chain rule for now the error at a specific time step t. So again, we may have a long document. We have 500 time steps, and now we want to predict the 501st word. So now, in order to do that, we basically will have to sum over all the previous time steps that we had, and then apply the chain rule here. So we'll have the partial of the error at time step t with respect to yt, our outputs, and then partial of yt with respect to our hidden t. But now this actually hidden t is computed using all the previous hidden states at previous time steps, right? So we'll have here, we'll have to basically sum over all of these, and each of these will have w inside in order to compute that hidden state. So now, of course, that particular element here, ht of hk, will also have to have the chain rule, right? Because the partial of ht with respect to hk, which is smaller, we'll sum here from k equals 1 up to t. So now, again, remember, this is how we computed our hidden state ht. It basically is just going over this. So now we have the chain rule again, because here we'll have ht is basically dependent on ht minus 1, which depends on ht minus 2, which depends on ht minus 3, and so on, all the way to k plus 1. All right, now when we try to take this derivative here, hj and hj minus 1 are both vectors. So when we want to write that out, that basically becomes the so-called Jacobian, which is basically just a matrix of all the first order derivatives. In each row here, we'll basically have the first element, so hj1 in our case, with respect to all the elements of hj minus 1, comma m. So basically, this is just all the derivatives, but with respect to a vector-valued function f and a vector of parameters x. Okay, so now from the previous slide here, we basically wanted to compute the partial of ht with respect to hk, and again, this is the sum for all the previous ones, which again, in some ways, is just applying the chain rule. Now, in order to compute this Jacobian, what I would encourage you to do, it's really fairly straightforward, is to again derive each element of the matrix here. So when I define the Jacobian here, it basically boils down to having exactly each of these elements here. So for each element of m, you basically take the derivative with respect to all the other elements of j minus 1 of n. And if you write this out here, you can basically see immediately how you can ignore this part, because h doesn't appear in the second part of the sum. And then here, again, you could write out, in order to compute hj, the jth element, you look at the jth row of w, you have an inner product here, you take derivatives, and you write out your inner product in terms of a sum, and you'll quickly see a pattern. But then there's a sort of another trick that we haven't really discussed that much, which is how do you create from that pattern that you'll observe once you take these derivatives here, how do you actually get that into a nice matrix formulation? And this is one such trick here, where basically the derivative of each of these with respect to just the previous hidden state will be W transpose, that one is pretty similar to what you've derived before, times the diagonal of f primes. So f here is again just f primes, right? And so the diagonal of this derivative vector here is basically in this notation where we define all the elements on the diagonal to be exactly the elements of that vector, and all the off-diagonal elements are 0. And this will allow us to exactly define this hjm of each of the elements times the f primes here. And again, this sounds a little hard, but once you just write all this out and you write out, a little example matrix of, 2 by 2 or 3 by 3 hidden states by hand, you'll see that this is, somewhat clear. Yes?
What was the z?
Sorry, z is just the definition here of the diagonal. So it's just to define what I mean by diag. So in our case here, this would be the diag of f prime of hj minus 1. And then you have here at each element, the first one would be f prime of hj minus 1, comma 1. All right. Definitely do check at home that you make sure you understand, how this diagonal matrix formulation came about, and how you actually show that this is indeed gives you each element of this matrix. And again, in theory, we could have used the same backpropagation that we did before, but here we're trying to analyze and really point out how the vanishing or exploding gradient problem comes about. So we'll actually take this where you could, in theory, compute these Jacobians, but it's just very inefficient to create these large matrices, and the standard backpropagation formulation that we had before will be much more efficient to implement. Yeah. Another question?
Product, like matrix product or element-wise?
This is still just a matrix product. So whenever we would have
the product over like J, for example.
these are also matrix products. Yep.
So it's just going to be a big sequence of matrices.
Exactly. This will just be a big sequence of matrices. Yep. And in fact, now we can look at or try to remember our knowledge of norms or matrix norms, and we can analyze this matrix and the matrix multiplications. And so one thing that we know from the norm is that when you have multiplication of two matrices, then the norm is always larger for the norms of the two matrices separately. And so now we can basically define two beta values here. Beta is just a number we define now. We can compute that, for instance. We take our W, we know exactly what our W is, and we just take the norm of that. So the simplest one, L2 norm, for instance, we would just basically sum up all the squared elements of the elements of W here. And now this one is also easy to compute an upper bound for because we know f prime, for instance, in the case of the sigmoid or the tanh can only be so large, right? It's in the case of the sigmoid, it's like sigmoid of x times 1 minus sigmoid of x, right? And both are between 0 and 1. So we could basically define here the upper bound for each of these Jacobians. And again, the Jacobians just being the derivatives, all the single derivatives written out in a matrix. So now we can basically say that the overall gradient that we want to have for an ht with respect to an hk that might be multiple time steps away is a product of these Jacobian matrices. And each element of that product is associated with one step in the forward computation. And so when we compute an upper bound for this here, we can basically plug those in. It's the same W, and this is one of the problems, the same W here at every time step. And we can also very easily define an upper bound for beta h. And then we basically repeat that t minus k many time steps. So now if your k is very small and your t is very large, you basically have here a very large exponential where if now your beta W, your matrix, the norm of your matrix, the elements of your matrix are very small, then you will quickly take the 100th or 200th power of that very small number, and basically very quickly goes to 0. Likewise, if your matrix weights are actually very large, and you have here different kinds of nonlinearities, for instance, not the sigmoid, but maybe rectified linear units that just are linear for when the input is larger than 0, then it could get very, very large. And so that basically breaks the locality assumption that you do when you do gradient descent. So what do I mean by the locality assumption here? So generally, when we have some non-convex decisions and we now make a gradient step here, and we assume that with one small step in the right direction, we would just minimize it. But now it's such a jagged landscape that really what could happen is that from here to here, it is actually it is not as smooth, but actually goes, like this. And so then you make one little step, and actually instead of minimizing here, you basically blow up and your error is much larger. Yes?
Could you say again what the mathematical reason for the exploding is? Why that?
Sure. So basically, if the norm of your matrix W is much larger than 1, then here, and let's say your beta h is also just around 1 or slightly larger than 1, then you have 2 to the power of, and now some number of time steps. Let's say t is 200 and k is just 5 or something. So then we have 2 to the power of 195, and that blows up very quickly. Yes?
Isn't that just an upper bound?
That is an upper bound, but it's actually something that really happens in practice. And yeah, so either your W is very small, or like it almost doesn't matter how, like as soon as it's less than 1, it will go down a lot. As soon as it's larger than 1, it will go up very quickly. Yes?
Is the vanishing or the exploding phase more problematic?
They're actually both problematic, but the exploding gradient one, if you don't deal with it, it'll just immediately, after a couple of time steps, your gradients will go to not a number because you run out of floating point operation. So in that sense, it's more dramatic. However, it's so dramatic that if you have it, you immediately notice the problem, and then you try to fix it. The vanishing gradient problem is you think things are working, but really aren't capturing it. So when does this really when is this really problematic? Basically, if you have long-term dependencies, and I'll give some intuition very soon. Right, which is right now. Basically, but any other questions sort of about the math before we go into some more intuitions on, yeah.
It's a little unclear to me how the exploding gradient would happen in a case where you have these sort of saturatable nonlinearities, where like it's just kind of seems like if the magnitude of the hidden state is growing, then eventually you saturate and then your gradient kind of flatlines.
So the W though, no matter what your nonlinearity is, your W can have a norm larger than 1.
Nice.
And then if that the upper bound for this doesn't isn't very, very small, then you'll still have trouble. All right. So basically, when is this really a problem in practice? Almost all the time, largely for the following reason. So the error at a certain time step, ideally can tell you something about what to do in previous time steps that are maybe many time steps t away during backpropagation. So let's take a simple example here for the vanishing gradient problem for language models, where ideally words that happen many time steps away will have a potentially still big impact on the word you want to predict in the next time step. So let's say we have here Jane walked into the room, John walked in too. It was late in the day, and really here you could add a bunch of other things about the day and what kind of room it was and so on. And then Jane said hi too, right? And now John happened multiple time steps away. In this case, only like 5 to 10 or so, but really it could be 50, right? You can talk a lot about the room first, and then you would still ideally predict that she would say hi to John. And if you would like to train the model such that now you want to lower the error, and the error is basically measuring how well you can predict that she would say hi to John, and now you have to propagate each of these will basically be corresponding to a hidden layer, and you have to go all the way back to here, and then tell the model that if you see some a name, then after you go through many time steps, and then you see a sequence such as another name said hi to, you would want to give an increased probability to the latter name, right? And in theory, the models could pick that up, but in practice, that was very hard to do for a lot of people. And that is largely because of these vanishing and potentially exploding gradient problems. So to give you a little bit of intuition and also to bring those people up to speed who had trouble with the first problem set, let's go through a simple example of a clean neural network implementation. It won't be a recurrent one because that's what you'll have to do yourself in the next problem set. So we'll just go through one that a standard neural network but with 2 hidden layers, which even standard ones will have the vanishing gradient problem. They less often have the exploding gradient problem. And then we can also compare sigmoids and ReLU units, which will, especially for recurrent neural networks, will be very useful. All right, so let's go through this IPython notebook together. So, and I think we'll share this also on the website. So you can go over this and see a somewhat clean implementation. This was done by Namrata, started from something that Andrei Karpathy had written for a previous class, and then I'll just modified it a little bit. So basically here, okay, we'll just set up some plotting. Now we create a data set. It looks very simple. Basically, it's this spiral kind of data set, and we color here the different points based on what classes they're in. So we assume here this part of the spiral is one class. We have red, blue, and yellow. And now we define two types of nonlinearities here, the sigmoid and the gradients. And again, the ReLU here, which is just maximum of 0 or x. So very simple function, and the gradient here is so simple we don't really need to define it. It's basically 0 or 1. Oops. And now we'll define a 3-layer neural network. This will be a very simple definition here. We'll basically say, all right, we have a couple of 100 points per class. Well, this is not part of the neural network, but then our dimensionality of the input is just 2-dimensional, and we have three of these classes. And so now that basically define, like we'll say our first hidden layer is 50-dimensional, and our second layer is also 50-dimensional. So that's a lot of dimensions for 2-dimensional input. We'd assume and hope to be able to overfit this very easily. Now we'll just define here our model and all the hidden sizes, and then we'll basically initialize all the weights. Sometimes I prefer actually initializing it by having a uniform in a small range, but you can also use Gaussian initialization, maybe make them a little larger than they are by default. Initialize all your biases to 0. All right, so now let's go for 50,000 time steps. We basically do forward propagation. Forward propagation is simply, W1 times X plus B, just as we defined, times an element-wise nonlinearity. And then we do the same thing for the second layer, W2 times that hidden state plus B2. And the last layer here, in our case, will first compute these linear scores by W3 times the hidden layer activation plus B3, and then we exponentiate that and divide by the sum of all the exponents. We could have written this out also as a separate softmax function. Is that clear so far? Are there any questions? All right. And this is ideally, this is how simple this is in the end, right? Like a 3-layer neural network, and forward propagation is literally 3 lines if you have the right kind of auxiliary helper functions defined properly. And ideally, when you implement this in next problem sets, this is also how simple it is. I love code where you actually see the equations from the lecture in the code. All right, so now we compute our cross-entropy loss and compute our regularization. All right, now we'll go and do backprop. Let's look mostly for the case of the sigmoids. We basically have exactly that main equation for internal layers that we described before, which is W2 transpose times the delta messages, the delta error messages, and then element-wise multiplication of the f prime of the hidden layer. And simpler versions for the very first top one, where you just have the gradient times. I guess you can already have your deltas from your scores, which in the case of the sigmoid was just the target minus the prediction. All right, so now here we have our standard delta, which standard backprop that would derived in detail in previous lectures. All right, and now basically one thing we want to plot here are the derivatives of the weights of the first layer and also of the second layer. And so, and then we'll make all our updates with SGD, and then we'll evaluate training accuracy here. All right, so now we ran this with the sigmoid network and with the rectified linear network. And here's basically like a simple plot of the differences in the norms of the gradients of the two layers. So the top layer here, the second hidden layer before or after the softmax has a larger, much higher, gradients over time, much larger gradients over time than the layer below that, the first hidden layer. And now imagine, you have here some gap between those. Now imagine you actually repeat that 50 time steps, right? It'll just get smaller and smaller and then goes to 0. The same is actually true for the rectified linear. However, there you have some things that go to 0, but others go perfectly fine through the network. So that's why rectified linears actually often have less of a problem with the vanishing gradient problem. They're much more likely to actually have the exploding gradient problem because you don't multiply the output. The output is basically max 0x, and so this x can get very large, and you never cap it as you do with the sigmoid. But in general, there's still some that go to 0, and so it does decrease compared to other ones. OK, so now basically both can very well overfit this kind of simple data set with such a powerful neural network. Here's the sigmoid, and for the rectified linear units, you kind of see a little bit more sort of straight lines, especially if this was a single layer unit, like rectified linear. A single layer neural network with rectified linear units as a nonlinearity, you'd see sort of more straight lines coming from this kind of nonlinearity. And I encourage you actually to potentially take out one hidden layer here and then see how well both of these models could still predict this simple data set. All right, are there any questions about this example? Yeah.
So sorry, were the weights on each hidden layer the same as example?
No, sorry. This is like it's not really a recurrent neural network. These are two different sets of weights.
Same problem still happens even.
Exactly. Yeah. It doesn't happen. It's less likely to happen, but it's still it'll still happen. Basically, that was the problem. So deep neural networks have existed a very, very long time. And only in 2006, Jeff Hinton and Ruslan Salikutinov, his PhD student at the time, were able to make a deep neural network work at all for anything. Before that, they're just in theory so much better, but in practice, nobody was able to really optimize them because of these problems. And that was despite the fact that there are different weights at each layer. It's just even more amplified because in recurrent neural networks, you essentially have deep, the depth is like 1,000, right? Whereas in most neural networks that have different sets of weights, you usually have like 2 to maybe 5, and I guess now for some convolutional architectures like 20 layers, but never thousands. Yeah. Great question. Yeah.
Could you go back to those two plots to see the relative position of the blue and green?
Uh-huh.
Are they different? So this one green is on the top.
Uh-huh.
And then for the next one. So both of them, the second layers is larger, have larger values.
Mm-hmm. Yeah, so the gradient here, the main error that you have is at the top of this network, and then as you go down, it basically vanishes as you go deeper and deeper.
Goes down, you mean it goes to the closer to the end? Or?
Yeah, so we usually call this here is the highest layer, and this one is the first layer. So this is H1, H2, H3. All right, are there any more questions? Yep.
Are you going to share this Python notebook?
Yeah, we'll share the Python notebook on the syllabus. All right. So, yeah, you saw one plot, and if you just initialize it again, it may actually look like this. So it won't look exactly the way you saw it, right? Depending on the random initialization, like we know we have these very non-convex kinds of energy landscapes, and so in some cases, this is what it looked like. All right, so now that we know what the problem is, how do we actually fix the problem and not suffer from that and actually get these models to work well? So far was the theory, now is the maybe not as beautifully justifiable practice, which is that one way to deal with the exploding gradient problem is the so-called clipping trick, which is really just saying we'll have a maximum value for every element of our gradient. It is really quite hacky. So you just say your gradient is 1,000, let's just set it to 5. No matter how big it is. And so that's really it. And there's so much math that went into this, and so many people tried something, and then Tomasz Mikolov here just said, well, let's just set it to 5. And literally 3 to 5 or so is a good maximum value for the gradient. Yeah.
Does it make any sense to try to normalize the error messages like they do with these link propagations, for instance?
Yes, and there's some interesting sort of batch normalization kinds of ideas, but yeah, for RNNs, this is the default thing that everybody uses. Yeah. Nobody has tried that yet for recurrent neural networks to try to normalize the error messages. The problem is, like, when you normalize that, you also mess with the gradient in even weirder ways, right? Now all the gradients of all the different elements of the gradient modify each other, and you might not necessarily want that, right? Maybe what you have is you have a gradient that is very, very large in, so let's say your gradient for your entire theta is mostly reasonable values, but then one thing is just 1,000, right? And all the other values are actually reasonably sized. Now that will just really mess up your thing, because once you update one of the weights to that, it will basically screw up everything else, and you get not a number very quickly in your implementation. And so now we'll just set this to 5. This was quite unsatisfactory, but was what actually worked for a very long time. And so one nice paper out of Joshua Benjo's group is basically tried to analyze a little bit, at least, what's going on here, and they implemented a very simple recurrent neural network. And this is actually something that I encourage you always to do too. If you want to gain some intuition of what's going on, you can always just implement a tiny, tiny network and then see really exactly what happens to every single number in your network. You can visualize it and so on, and this is what they did here. So basically, they had a single hidden layer, sorry, not a single hidden layer, but a single unit recurrent neural network, but many time steps. And they basically just wanted to predict some output, but it depended on some time steps, many steps before. And so as they visualized, this is basically exactly this sort of non-convex kind of decision surface that we have. So this is our J, for instance, cross-entry pair, something like that. But in this case, with vocabulary of size 1. Well, I guess the softmax could have whatever, any number of weights, but here we basically just plot the values of W. So each W here has specific, and the bias term here basically comes with a specific element of your energy landscape here. And basically, the solid line that you see here is what happens when you do your standard gradient descent. And after you hit this high curvature wall in your objective function, basically jumps all the way somewhere else, and it's totally messed up. Whereas when you rescale it to a fixed size, it basically doesn't jump around that far and stays somewhere where it's reasonable to in the end, try to minimize this error here. So imagine you try to minimize this error. You took a tiny step here, and now it sends you all the way somewhere entirely different. So this is at least some intuition of what we gain from the gradient clipping. Yes?
If you have more than one hidden unit, does that increase the number of matrix walls? Or like, what is the intuition? What's the intuition behind adding more units to this representation? What would happen if you added more?
So the question, if I understood you correctly, is what's the intuition when you have multiple hidden units in the recurrent layers? I mean, basically, we think the same kinds of curvature walls happen, but just now in a much higher dimensional space. And we can't visualize them anymore. Yeah. Yes?
So, say your parameter have a lot of dimensions. Do you just scale one of the dimensions that is pretty large and keep the rest the same?
Yes, you could do that. So the most common one here, they have a slight modification to that, but the most common one is literally to just have your gradient. Each element I of this is just the max of, the minimum of 5, that gradient. Yeah. Yes?
Where's the actual minimum when it's energy surface? Is it the crease between the...
Yeah, exactly. It's somewhere down like right here.
Okay, so if you kept on optimizing, you didn't change the learning rate at all, even with the clipping, so you would essentially hit the minimum and then hit the wall, but then you wouldn't jump back as far. You would just keep doing that.
Exactly. Yeah. And that is, again, for one dimension. You would probably think it's even more complex, and maybe there's some crevices and so on. Cool. OK, so that was the trick to solve the exploding gradient problem. Now, the vanishing gradient actually also has a couple of different people have different ways of trying to fix that. There's actually one that seems very promising that just came out in its latest sort of version literally 2 weeks ago by a friend of mine, Kwok Lee. Basically, two things. One, we can initialize our hidden to hidden W to be the identity matrix. That is the first thing. That way, as you combine the next step, you kind of just average things in the beginning, and then you go from there. And the other one is to use the rectified linear units instead of sigmoid or tanh units. And the rectified linear units, essentially the derivative is either 0 or it's 1. And when the derivative is 1, you can nicely propagate that error through to previous time steps. And if it's 0, you just stop, and that unit is basically gone. But for those units that aren't set to 0, the gradient nicely propagates all the way to previous time steps. And so here's one plot for a somewhat artificial problem. I guess I can briefly talk about this. This is basically a pixel by pixel permuted MNIST. So MNIST is a very simple data set of just digits. Deep learning community had worked on it a little, far too long. And here, the main problem is you go over all the digits of the pixels, and each pixel is one time step. And then you try to essentially predict what the number is in the end after going through all these time steps, right? So you have like 700 or so pixels, and you go through 700 time steps. It's a very artificial problem, but it's still kind of hard because you need to keep around, what have you seen before in like 100 time steps before. It makes the problem artificially hard, but very easy to analyze. And so if you use this identity initialized recurrent neural network, you basically can get much higher test accuracies than if you used a standard RNN with tanh units. And LSTMs, which work actually incredibly well in some problems, and we'll cover them soon, do better than these other methods, but not as well as this simple trick of just identity initialization and rectified linear units. But that's, again, just for this particular synthetic problem. This was actually an idea that I first introduced, but in the framework of recursive neural networks, which we'll also talk either next lecture or next week about. And then again, there's some new experiments with recurrent neural networks just 2 weeks ago. Yes? So one, I guess, when we looked at all these Jacobians, right, we had basically it's close to 1, the norm. So that's one. And I guess the other one is that when you initialize the entire matrix completely randomly, then your first sort of transformation from this hidden layer to that other hidden layer is a completely random projection, right? Like you have a bunch of random numbers, and you basically randomly project them to the next hidden state. If it's the identity matrix, then what happens here is basically that it's just going to be this plus, and let's assume this was also the identity matrix, right? Then this would basically just be an average times 2 of the current word vector and the previous hidden state. And so that essentially doesn't as randomly project your hidden states as it would if you just had a bunch of random numbers in your WHH, and basically make sure that your current input really has a reasonable modification to its hidden state instead of a completely random projection in the beginning. So in the beginning, you kind of just average out a bunch of stuff. I think in the recursive neural network setting, it's actually even more intuitive, and we'll get to that soon. Yes?
So you talked about like nonlinearity choice and this gradient clipping thing. What about like regularization? Are there forms of regularization that can specifically target the vanishing or exploding gradient problem?
So you do usually have your standard L2 regularization on all these weights as well. And you would hope it helps, but it can't help enough because of these many multiplied Jacobians.
Yeah, I mean, I'm just wondering, like, it seems like you want to, like, these things seem to be suggesting you want to, like, kind of weakly enforce some constraint on, especially the recurrent matrix, like that it should kind of weakly belong to some family of matrices.
Right. Yeah, you could maybe try to have some interesting norm regularization on something. People tried a lot of different things. So one of the things we, I guess, had skipped for time constraints is dropout, for instance, where you basically turn off half of your hidden units randomly, and then you multiply your weights at test time, or you divide them by 2. And so that actually doesn't help for recurrent neural networks either. So at least there's one paper that suggests that it's not very helpful. Yes?
To what extent are exploding gradients a problem with this initialization? Or does that solve that as well?
I think they might still use the gradient clipping to deal with that. Cool. Okay, so we talked about sort of traditional count-based language models, and the one that works best. We don't have to go into the details because it's not going to be that important for the class, but it's called Kneser-Ney. It's a specific type of smoothing and a combination of backoffs, and really beyond 5 grams, nobody can keep around. Nobody had enough RAM, especially not in 2011, to keep around these kinds of language models for more than a window of 5 words before. And here is basically a baseline, and again, this is the perplexity, and this is on 2 different corpora, the pen tree bank, and the switchboard, which is a corpus for speech recognition. And the lower is better, and here we have basically the traditionally best method with 141 and a recurrent neural network trained with backpropagation, which is called backpropagation through time, but really it's the same kind of delta messages that we've computed before. It's just, again, matrix derivatives. And it basically has a much lower perplexity on both of these data sets compared to the previous one. And so, why does this work? I guess another level of intuition here is that these word vectors are very powerful, right? And instead of having to see exactly, you know, I loved my pet cat something, I could now, like, seeing I love my pet cat and I love my pet dog are very similar to a neural network, because cat and dog have similar word vectors. And the word vectors here can also be learned in the recurrent neural network. So in all the equations that we wrote out here, we could take derivatives with respect to x also and actually learn word vectors through a recurrent neural network. We don't have to always just use you know, Glover word to vec and initialize them. We could also initialize the words randomly here and take derivatives with respect to x. But basically, as we do that, similar words have similar vectors and hence similar probabilities for being seen, and that helps the perplexity. We can basically give I love my pet dog a higher probability because we have seen I love my pet cat. All right. Yeah.
What's the difference between the RNN trained through by backprop versus backprop?
I actually think that it looked like originally in his early papers he kind of propagated only a certain number of time steps by hand, but really, and this is I guess something I'll mention here, which is you really need to only do one pass backwards through your entire sequence once. So what do I mean by this? So as we have here our hidden layers, right, and we have forward propagation, now I have a new error at every time step. So at EHT minus 1, ET minus 2, and so on. And now I add my deltas here. So these are my delta error messages, just as before with the standard neural networks. And now here I have a new delta message coming from this. And now instead of doing this once, propagating once this error through the entire network and ignoring everything else and making one update step, and then taking this one and doing everything, you can really just do one pass and you just add your delta messages as they come. And you know, each of these here now is basically the accumulated sum of all of these. And so originally, I think Mikolov didn't realize this trick and just propagated for a fixed set of time steps. All right, so one problem that these generally deep learning models have when it comes to predicting the entire vocabulary is that the larger your vocabulary, and ideally you want to have your vocabulary be millions, the larger your final matrix multiplication is for your softmax, right? The softmax has number of outputs, number of rows is the number of words in your vocabulary times your hidden unit. Now your hidden units might be 1,000 and you have 1,000,000 words in your vocabulary. So that's 1,000,000 times 1,000 dimensional matrix, and you have to multiply all of it all the time, which is horribly slow, right? There's a lot of multiplications inside. And so one way to deal with that is a nice trick, also coming from Mikolov, who really spent many years on just recurrent neural networks for language modeling. This was basically his entire thesis. And one neat trick is to basically use class-based word prediction. So you basically try to predict the word at time step t, given the history, but now you will basically factorize this and say, I basically first predict a class given the history, and then I predict a word given this class. So now the word given the class, let's say each class has maybe 1,000 words in that class, and I have 1,000 classes, right? Now I will basically have 1,000,000 vocabulary, but for one class, I only need to do backprop and multiplication for exactly that class. And in our case, the history is just the previous hidden vector ht. And so if you have the number of classes is the same as your vocabulary, then you don't gain anything. And with fewer and fewer classes, you basically can get a nice speed up, but also you have a drop or an increase in your perplexity. Yes?
How do you estimate the P of the word given the class? Is that do you also take into account the history, or?
No, it's just at that point, you just, for this class, you have, I mean, you could make it, again, a neural network and do it that, but usually you have a fixed cutoff in order to be able to ignore the entire rest of everything. So now you basically don't have to do this gigantic matrix product. Okay, I already covered that one. So now one nice thing is we've talked mostly about language modeling, and this really only because it's a nice basic task. In some ways, it's actually an intermediate task. You could assume in some abstract world, it is actually a task that solves all of NLP, right? If you could perfectly predict every word that comes after, that comes next, why not build a question answering system or a machine translation system that asks what's the translation of the following sentence, and then it would, predict that translation. But in practice, that doesn't actually work. The language models, for the most part, are only able, even the recurrent setting, even this, in theory, we could keep track of all the history. In practice, the history is not 5 like with traditional models, but maybe 7 to at most 15 or so. And after that, we can't really take into consideration what happened before. But these kinds of models are a lot more useful for basically any other task, and not just predicting the next word, but also predicting for every single word some kind of output. So the task that we've looked at before a lot is named entity recognition, or NER, and we can use recurrent neural networks also to predict named entity tags. So at every time step, instead of trying to predict the next word, we can just try to predict a specific label. We can do that also for entity level sentiment. So let's say you have something like, I like the screen of the iPhone, but I didn't like its keyboard or something. Now you can say screen is positive in this context. And now the recurrent neural network can capture that context for you and classify that word in, well, so far in our standard RNN only based on the left context. One particular example here comes from Ozan Irzoy, who's a PhD student right now at Cornell. Well, right now he's an intern at MetaMind. But and so he's basically published this nice paper last year on opinion mining with deep recurrent neural networks. And so what does he try to classify? Basically, he tries to classify each word as belonging to either of 3 classes. The first one is none of the above, not an opinion word. And the other 2 are a direct subjective expression or an expressive subjective expression. So what do I mean by this? Basically, a DSE, or direct subjective expression, is an explicit mention of a private state or speech event. And an ESE, or expressive subjective expression, is an expression that indicates some kind of sentiment or emotion. So like, awesome is a positive emotion, but without explicitly conveying them. So let's look at an actual example. So here we have, for instance, the committee, as usual, has refused to make any statements. So now, as usual is essentially an expression that indicates some sentiment. In this case, it's kind of negative. And here, has refused to make any statements is basically direct subjective expression. So one commonly used notation that you should know is the bio notation, which is a way to describe the labels for every word such that you can actually also label longer phrases. It's a very simple one. It basically has 3 types of labels: the beginning, B of any kind of type of tag, and the continuation of that kind of tag, I, and O for none of those kinds of labels. So as usual is the beginning of an ESE, and to as is the beginning, and usual is the continuation. And this whole phrase has basically one specific label as well. So now the recurrent neural network that he defines is very similar to the one that we've defined before. And I'm trying to use the notation from the paper so that you can kind of start to see past the specific W superscript HH, for instance. So our W superscript HH is his V, and our W superscript HX is his W here. So don't be confused. What we define for our vanishing gradient formulation, for instance, we skipped here. We had W was the HH instead of being the 1 multiplied by X. But once you see X here and once you see H here, you can kind of know which W's and what the parameters mean and what they're used for. He has the same notation F for nonlinearities, and instead of writing out softmax here, he uses the function G. And his softmax weights, which we often use W superscript S for him is a U. But once you see, oh, he has a recurrent neural network, and you see those equations, you should kind of be able to just see past the syntax and understand that we really have the same semantics here and the same kind of model. And instead of having lots of little dots here for each vector, he describes each vector as just a single dot. Again, you'll observe that in the literature a lot. But other than that, the H is still sort of our memory that is computed from past memories and so on. There are two interesting tricks and modifications to the RNN that he didn't necessarily invent. There are other people who have introduced these before, but he had used them nicely for a different kind of task. The first one is the idea of having bidirectional recurrent neural networks. So instead of just having your hidden state be dependent on the left side, you now have another recurrent neural network that just basically turns around your text and goes from the end to the beginning. And so you have HT forward or left to right, which is basically a standard RNN. And you have an HT right to left, which is also a standard RNN that just happens to go in the opposite direction. Same idea, same equations, same math, same backpropagation. You just backpropagate past each other. And your final prediction can now come from the left pass and the right pass. And again, backpropagation, everything is the same. We just take matrix derivatives here. And now comes the second modification, which is you can have a deep bidirectional recurrent neural network. And now you start to understand why you really want to understand, why you just want to have this intuition of, oh, I have my delta error messages, and they just come from various places, and I just add them, right? And this is why we went through these first basic ingredients and basic Lego pieces so carefully, because now it just goes, models become more and more complex. But again, it's just a bunch of matrix multiplications. It just happens to be that for a certain state in the forward propagation, if it's in a higher layer, it will now depend on the previous HT minus 1 as well as the HT of the layer below at the same time step. And maybe at this point we'll stop and we'll look at his evaluation and so on in the next class. Thanks.